So, today we will be discussing about planar graphs. Have you heard of planar graphs? By planar what we mean is, we should be able to draw the graph without crossing the edges, that is if at all there is a cross it should be on the vertex, right. So, I mean there is a edge means what? They can intersect only at vertices, two edges can intersect only at vertices. So, that is the simple plain language that we can say about a planar graph. So, what kind of problems do we face in this? Like now you should be having a rough idea, you take any topic, there are hardly 3 or 4 types of problems that we have been seeing. What are the problems that could exist in a planar graph in this topic, under this topic? What do you expect? Coloring? Oh, okay, first about planar graphs. First about planar graphs, then we will go into something more about it. Coloring is also one type of problem that we can deal with it. So, you all have no clue at all what will happen. I throw you a planar graph and I say it is a planar graph, you all will accept it, right. So, I can take it for granted. That is not going to be the case, we have to anyway verify, right. So, that is what you have been doing, studying decision problems to verify something is true or false, right. So, same way here also we need to decide whether a given graph is planar, that is one kind of a decision problem you can think of. So, the first question is we want to answer whether a given graph is planar or not. So, when will it be planar? So, we want to decide on this necessary and sufficient conditions for a graph to be planar. This will be the first problem that we want to attack on, and then how to test the planarity. Okay, planarity testing is another big challenge that is there still, like given large graphs, how do you test for it? Okay, how to test for planarity? I mean once you have this first question answered, second might look easy, but again the problem is to test in effectively polynomial time, right. That is what we want to do. Can we do it in polynomial time or do we require more time to do it, more than polynomial, exponential, or is it NP complete? So, we should also decide about all these kind of issues. So, the major question is how to test for planarity. And last but not the least, if you want to test, you have to give me an algorithm, right, for testing, as well as you should give me a plain graph diagram, right. You have to give me a solution. Okay, this graph is planar because I can give you a structure where it is going to be plane, right. I mean where I can draw it in plane, right. So, the third problem, like still there are some work here in this direction where you can work on. So, design a algorithm, preferably polynomial time, to draw a plane graph. So, we will see what these terminologies mean. Okay. So, what do we mean by planar, plane graph, all these questions we will try to see. If possible, we will enter into second and third question if time permits today, because this whole topic in each itself can go for many lectures. Okay. So, this 3 will keep as target, but I will try to touch upon each of them. So, the first part, definition of a planar graph, as we have seen. So, if the graphs do not cross, I mean if two edges do not cross, then we say it is a planar graph, right. So, if no two edges cross or intersect, I could say, I mean I am giving you a loose word, so do not take this as a formal definition, it is just for your understanding I am giving. Cross or intersect other than at vertices, right. Okay. So, a graph is also said to be a plane graph if the drawing itself shows us that it is like what to say, by structure I can say that it looks like there are no two edges crossing. Okay. If that is the case, then we say that the graph is a plane graph. Okay, it is simply a drawing of planar graph such that no two edges cross. Okay. So, say for example, suppose I give you this graph. So, is it planar? Yes, right. So, I will make it look non-planar. What about this? Okay, so let me remove this. How about this? It is a planar graph, right. So, this is a planar graph, but it is not a plane graph. Okay. So, that is the difference that I want to tell. This is planar. A graph, we know it has an embedding into a plane, right. So, then we can call it as a planar graph. So, what will be the plane representation for this? I think I just have to pull out one edge, right. This edge I just need to pull it out. So, if I want to draw the plane graph for this, I can just pull it out, right. So, everything is in the plane, right. I mean there are no two edges that cross except at my vertex set, right. So, this is a plane representation, or we call this as simple plane graph. So, to answer our first question, necessary and sufficient condition, this question was answered in positive by one of the famous mathematicians and graph theorist, I should say, Kurtowski. I think I am right with spelling. So, he proved it in 1930, okay, that he found a condition where using that we can just simply say that if these conditions are satisfied, or if it is not satisfied, then the graph is planar or non-planar. So, how did he prove this? The idea what he used is the hereditary property, the idea of having an hereditariness in every graph. So, what is a hereditary property? So, what do you understand by this word hereditary? So, the property, suppose there is a property P that is satisfied by a graph G, right. Then if that property is satisfied by every subgraph of G, then you say that it is an hereditary property. It is like you have it and your children also have something like that, right. It usually we have such kind of things, right. Hereditary means it comes over generations, we say. So, in similar language we can say that a property P is hereditary if every subgraph of G has it. If first of all G should have, and then every subgraph of G also has. I will say a property P of G. Okay. So, can you tell me one hereditary property? This is a hereditary property for the graph, bipartiteness. So, can a subgraph have suddenly an odd cycle if the original graph does not have? So, that is not possible, right. So, bipartiteness is one hereditary property. Anything else? Complete graph. So, will a subgraph of complete graph be a complete? Why should it be? I can just take a path P3. You did not say induced subgraph. So, I can take any subgraph. No, that is what, see, the property what you are saying is, that is my given graph is complete, completeness is a property you are saying. So, does that mean that every subgraph has that property? I am not saying induced subgraphs. I will take, see here, suppose you are talking about this completeness and I delete this edge, is it complete? This is a subgraph of Kn, right, K4. This is not hereditary, this is not complete, right. So, completeness is not a hereditary property, right. If you say induced subgraph, then it may be a hereditary property, right, or only for induced subgraphs, but this is not induced, right. So, before we go into the proof of this, I mean statement of this, we will see some necessary results that we need to go through. So, how many of them have heard about this in any other context. So, a Jordan curve theorem states that, I mean it was stated by Jordan of course, any closed curve in a plane, okay, divides the plane into 3 parts. Okay. So, one is the interior of the curve, any closed curve you take. This actually comes from geometry, you can think of this. So, suppose we have a closed curve, then this closed curve divides your planar region wherever we are talking about into three different domains I can call. Okay, so, one is nothing but this interior part, the bounded region. Okay. So, this is called as interior of the curve, and this portion is called as the exterior of the curve C, and the curve itself is there. So, that curve forms the boundary for these 2 regions. So, that is why we say like it has 3 parts. Okay, one is the interior, one is the exterior and the boundary itself, right. So, if you look at this, you take any 2 points, any curve connecting these 2 points will have to cut through the curve, right. So, so this is what Jordan theorem states in geometry. So, if I want to translate this into graph, well, how do we translate it into graph language? If I have a planar graph, right. So, a planar graph, this sides, the edges of the planar graph, okay, divides the plane into 2 regions. One will be the interior of the boundary that it is covering, and the other one is going to be the exterior, and the boundary itself, the edges, right. So, when I say 2 points and a path connecting them, you can think of a path in the graph that connects the 2 regions, okay, and or edge at the worst case, right. So, this is what Jordan's curve theorem states, that given any curve, any closed curve, we can divide it into 3 different parts, right. So, coming to our problem here. So, let me just draw a graph. So, how many regions? So, every region here we will call it as a face. Okay. If there is a closed path, say this triangle is here, right. This triangle divides my region into 2 parts. So, the one is the interior and the other one is the exterior. So, here what we will call is, we will call it as a face, okay, because we are in planar region. I can call each of this region as a face. Okay. This will be like interior of the face, interior face, exterior face and so on, okay. Because we do not have a curve, instead we are talking about edges connecting them. So, we will call it as a face, and this edge, suppose if we are looking at this triangle, this is going to be called as the boundary of the face, and the boundary has 3 edges, right, for this face, okay. And if we have a cut edge, that is a single edge, an edge which is not going to be part of a closed region, then we usually what we say is it contributes to only one face, right. But when we count for the boundary for this exterior face, we will count this particular edge, the cut edge, as 2 edges, okay. Twice we will count it. When we count the number of edges that comprise the boundary, we will count this kind of cut edges or tree edges to be twice, okay, in counting. So, in connection to this, so how many faces are there here? So, how many faces there? 4, 5, 6, 7. So, any closed path or cycle, if it is there, we can say that the interior of that is going to be a face. 3, 4. So, first face is this, say let me label it as F1, another face is this loop, it has a face F2, and this is a face F3, then the outer unbounded face, right. Usually the unbounded face is what we call as exterior, okay. If it is a bounded region, then we will call it as interior. It has kind of a boundary to fix and the region is bounded, so we call it interior, okay. So, now can you tell me the boundary of each of this face? So, let me just write the boundary B of F1, What are the edges that comprises of the boundary? That is what I am going to ask. So, the 3 edges, okay, oh, I did not give you the label for this, okay. So, let me do that. So, in this case, then now I guess it becomes easy. The boundaries are 1 2, 2 3 and 1 3 or 3 1. Anyway, we are in undirected graph. Boundary of F2 7, right, the loop formed by this edge, right, or if I would have labeled this edge, then I can just tell this is the edge that we are talking about. So, actually I should also start labeling the edges, say let me just for definiteness now I will call E7, okay, the loop formed by 7, E7, right. So, what about F3? 4 5 sorry 4 5 5 6 6 7 7 4 4 8 8 9, right. So, now I see doubt why 4 8 and 8 9 are coming into picture, right. That is what I said, when we look into boundaries every edge is accounted for, right. So, now when we go into, of course, what about B F4, the boundary of F4, all the edges which are in the outer part, right. So, 1 2 2 3 3 4 4 5 5 6 6 7 7 4 and E7 is also there, yes, and 1 3, right. So, all these edges are there. So, now we will go into the next step of degree of a face. What is the degree of a face? You know degree of a vertex, degree of an edge, right. If I am talking about an edge, how many other edges are incident, we can still talk about degree of edge. In similar direction, degree of a face is nothing but number of edges in the boundary, okay, number of edges that are there in the boundary, okay. So, for F1, if you see degree of F1 is 3, right, and degree of F2 is 2. So, loop you can think that it is 2. What about F3? So, when we count the degree for F3, you have to count twice every cut edge, okay, because it contributes for two times, every cut edge contributes for boundary 2 times. So, if you count it, how many boundary edges are there? 8, right, 4 outer edges and 2 cut edges are there, you added twice of them. So, degree of F3 is 8. What about F4? So, do not just add it, okay, because number of edges are there, you cannot just like that add it, okay. So, here also like our first theorem in graph theory, you would have come across, sum of all the degrees of a graph is equal to twice the number of edges, right. So, here also we have sum of all the degrees of faces is going to be equal to twice the number of edges. Why? Because every edge will be a boundary for an interior region as well as exterior region, right. So, it will be counted twice, okay. So, in that sense you can see that sum of all the degrees of this graph, it should be equal to twice the number of edges. So, how many edges are there? So, from here also you can come to a conclusion if you are still confused about F4. I think I said E7 I am counting it twice, no, we will count it only once with to match up with this definition. I think every loop we have to count once for interior, once for exterior, only once. So, I said we will count loops once, so we will fix to that, we will not confuse more. Only cut edges we count twice, because cut edges like kind of it contributes from either side of the edge. Okay. So, 3, 4, 5, 6, 7, 8, 9, 10. So, this should be 22, right. 4, 5, 6, 7, yeah, 22, 2n, right. So, what is degree of F4 here? Still now nobody is giving me an answer. 10, right. 4, 8 and 8, 9, yes. I am giving you a plane diagram, this is the diagram that I give you. So, that means what? It should be, it is where it is, yeah. If I give you a different diagram so that 8 and 9 are outside, then those two edges will be a boundary for outer surface, outer face. But now I have purposefully drawn it inside, so it is going to be boundary only for interior face. That is, you might have a confusion, if it is a cut edge, it should belong always to outer face. There is no restriction like that. It can also belong to a bounded face, interior face. Okay. So, with this we will also go into another concept of duality. So, given any plane graph, okay, we also have another dual for this. Okay. So, the idea is what we do here is we will anyway consider this dual for other purposes also. Like yesterday I started talking about, when we talked about coloring, we said we want to do a map coloring, right. So, map coloring fits into this regime, right. So, given any map, obviously it is going to be planar because we have a plane embedding for that, at least in our spherical earth we can try to embed it, right. Any two dimensional plane we can just embed it there. So, if I want to give a coloring for that, I will also talk about the faces, converting it into vertices, and we can talk in terms of vertex coloring also. Okay, so, this is one kind of use purpose for dual graph, but it is not the sole purpose. So, what is a dual of a plane graph? Given a plane graph, okay, so we have a plane graph. So, that means what? Every plane graph has boundaries, faces like this part, right. So, now what we do is, for the dual you construct a new graph. So, this is given the graph G. Now, I am going to go in for dual. A dual is going to be containing of, say, vertex set and edge set V star and E star. What is happening here is, every face of my G will be now considered as a vertex for G star. Okay. So, my V star will consist of set of all faces of G. Okay. And you connect any two faces, say suppose we have F1, F2, say from the previous graph, if I take, say I just put V star is equal to F1, F2, F4, F3, F4, these would be the vertices now for my dual graph, and any two vertices in this graph is going to be connected if they share a common boundary. Okay. If they have a common boundary, then we can just connect these two vertices, as vertex. Okay. So, going back over here, I think it has already gotten clumsier. Okay. So, this is the graph I have given. So, suppose I will just, so this is going to be my, say, F1 star, a vertex. I am just plotting it in this itself, I am drawing the dual here itself. So, this is, say, F2 star, F3 star, and I have my outer region, say F4 star, just I am relabeling them, so that my vertices are going to be labeled as F1 star, F2 star, and so on, right. So, if you see, F1 star is connected to F4 star, and how many edges are there? How many edges should I draw? I said if there is a common boundary between two faces, I will draw an edge between them, right. So, here if you see, there is an edge between F1 star and F2 star, because it has one boundary here, not only one, in fact you can just see this is also another edge. So, along this you have another one, right. In fact, F4 star has a cut edge, right. So, that means what? It has a boundary sharing with itself. So, I should also consider that edge, it is going to be a self loop in fact for the vertex over here. And what about F2? F2 is obviously adjacent to F3, and sorry, F3 it is not adjacent because they do not share any boundary, right. So, they are not adjacent, but F2 has again common vertices with F4, right. So, we have to connect through all those edges we are talking about. Oops. am just trying to draw it, still keeping in mind that it could be planar, right. In fact, it is, right. And in fact, if you see F2 also has, there is one more edge I could draw here, right. F2 has cut edges, so there are self loops again connecting with itself, okay, through which is like it has a common boundary. So, this would be there connecting to F2 itself. Okay. So, this is now the graph that we are talking as dual. Okay. So, the dual, as you can see, it need not be simple anymore, it has multiple edges, it has loops also that are always possible here, right. Whenever you have cut edges, loops will be there, and of course, there are more than one boundary. So, you will always have multiple edges. So, this concept of dual, now whatever we want to study with G, okay, like we can do it with G star also. Again, we can use this G star as our gadget, like what we have been doing. So, we can use this in many places, this will come in handy, because vertex coloring we have lots of results, you can pull into it, study about it over here, and then you can translate it into original graph. Okay. So, this is one concept that we could look into in dual of planar graphs. So, the next one is about the number of vertices, number of edges and number of faces that a planar graph contains. Okay.